So this is a multiple choice practice test that College Board put together a few years ago. I don't know if it's a released version of one of the international. It's a few years old, but it's still worthwhile. It's very worthwhile because multiple choices are like practicing the many skill. When I say many, not MANY, the many small skills that you're going to need to put together for free response questions. So these multiple choices really are very important. Not so much, at least in the year 2020, when there are no multiple choice questions. The multiple choice strategies are not so much important, but the skill work of the multiple choices are extremely important. So I'm going to run through this with you. I think most of my workouts are pretty clear in their explanations, but I am going to just make some comments here. So in number one, I'm focusing on the antiderivative of the cosine of 3x. And remember, for integration, you have basically just a few strategies in an AB class. So the first strategy is what I would call a normal problem. Normal, like reversing the power rule. There's nothing unusual about it. There's no inside function. You just look at it and you know exactly what to do. The second thing that we often consider, and part of the normal would be like reversing a trig derivative or reversing a trig inverse derivative or inverse trig derivative. That is fairly obvious. In other words, you don't have to do anything to it. And then if the function is not normal, you're looking to see, is there an inside function? And if there's an inside function, we're probably going to launch into u substitution. And so in that case, you have to decide what u is equal to and du is equal to and so forth and so on. Some other things that you might run into are the possibility of complete the square. So don't forget about that. And look for situations where you have inverse trig. That sort of that's oftentimes where you'll see the complete the square come in the case, and you're also going to have a u substitution there. And then finally, long division is also a possibility that you might need to do before you can do your integration. But in this case, we have an inside function of 3x, so we're going to let u equal to the inside. We're going to take the derivative of both sides, and I do not need that coefficient of 3, so I'm going to divide 3 on both sides. I'm going to go back and substitute u in place of 3x, and in place of dx, I'm going to substitute a 1/3 in the front and a dx in the back. So that's my substitution here. The antiderivative of cosine is sine, and I always check that by asking myself, what is the derivative of sine? The derivative of sine is cosine, so I know I did my trig integration correctly, and then I'm going to resubstitute the 3x back in place and put my plus c. In number two, we're doing a limit question, and we're looking at a rational function. And one of the biggest mistakes that students make when they're doing a limit with a rational function is that they pay attention to the rational function, but they don't pay attention to what we're approaching. Most students start jumping into end behavior, either right or left end behavior, because they know those rules for finding the horizontal asymptote using top heavy, bottom heavy, and same heavy. Well, that's just not the case at all in this particular situation. So when you're finding limits, remember, the first thing you always want to try to do when you're finding a limit is direct substitution. However, we can see pretty quickly that if we substitute 0 in here, we'll get 0 in the denominator. So we can't use direct substitution. So now we're going to look at our strategies of limits, and hopefully when you look at this expression, you can see in the numerator and denominator there's a common factor. So I'm going to factor the common factor out of the numerator and denominator, and notice I have a removable discontinuity. I'm literally removing it. And when I remove the discontinuity, then it allows me to substitute 0 in place of x and get my limit, which is approached y value of 2. In number 3, we are trying to force the function, let me bring that up a little bit, force the function to be continuous. This problem does not ask us to deal with differentiability, so I'm going to substitute 2 in place of x. And when I substitute 2 in place of x, I get a y value of 7. And because of the equal to, I know that that's going to create a solid. That's definitely going to be a y value on the graph. Then I'm going to substitute 2, which is what I call my breaking value, in place of x again. And I get 2k plus 1, but that's going to be an open circle because there's no equal to. Well, I'm trying to force the function to be continuous, so I'm going to need to fill up that hole right there. Here's my hole. I'm going to need to fill it up with that 7. So the 2k plus 1 has to equal to 7. Therefore, k has to equal to 3. In problem number 4, be careful this time. In number 1, we had an integration of cosine. Now we are taking the derivative. We have, as you can see here, I rewrote the cosine cube so that the cube is on the outside with parentheses, so I can see that I have a chain rule. So the power of 3 is the first link in the chain. The trig function of cosine is the second link in the chain. And the angle, which often gets forgotten, is the third link in the chain. So I'm going to start by working on the power rule. So multiply by the power, decrease the power by 1, and leave the inside alone. That's link number 1. Link number 2 is to take the derivative of cosine, which is negative sine, leave the inside alone, because we're on the second inside. And then lastly, this is the part you don't want to forget, but often gets forgotten. The derivative of 4x is 4, and then we can multiply and simplify that. In number 5, we are in the work for number 5 is down here. In number 5, we're looking for a relative maximum. This is f original. So I'm going to find the derivative of f using the power rule, which is what I did here. I divided both sides by 6 because I have a common factor of 6. I carefully did my factoring and made sure that my signs were correct. I found a critical number of 2 and negative 1. I take those critical numbers and I put them onto my first derivative number line. I carefully do arithmetic by substituting into the first derivative. I'm looking for a relative minimum, and I can see very clearly that I have a relative minimum at x equal to 2. In number 6, and the work is right beneath number 5, in number 6 we're given an original function. It is a product that often gets overlooked, and it also has a chain rule in the first factor. Which of the following is the equation of the tangent line? Well, when we write the equation of a line, we know that our target is y, at least our first target is y minus y1 is equal to m times x minus x1, and then we can get y by itself. It says x equal to 1, so we know the x value that can be substituted, but we need the y value. To get the y value, we're going to substitute into original, so we're going to get f original of 1 by substituting in here. When you substitute into f original, somewhere it's right here, you get a y value of 2, so that's going to go here. And then we need the slope, so we're going to need to take the derivative of f. Like I said, it is a product and a chain. So I have the first function times the derivative of the second plus the second function, and here's my chain rule. I did the power rule, multiply by the coefficient of 5, decrease to the fourth, leave the inside alone, 2x minus 1 times 2. Now, it doesn't matter if you had these two terms reversed in terms of doing your product rule. Now, I really don't have to simplify this out. I did carry it through. You can see in my work here, I carried it through and I did one step of simplification. I didn't really have to do that because remember, all I'm trying to do is substitute a 1. I don't really care about the derivative. I care about the slope that I get using the derivative. So that simplification was not necessary in order to get my slope of 21, which I substitute in here, and then I get y by itself and choose my answer. Problem number 7. We are finding the antiderivative. Remember in problem number 1, I talked about the various methods. This definitely, when I look at it, I don't look and go, I know exactly what the antiderivative of that is. So I would say this is not normal. And so my next thought would be, well, I'm going to go to a u sub. What do I want to let u equal? There are a couple of things. Now, in this case, I could let u equal to the power of e, or I could let u equal to the denominator of e, which is the same thing in this case. So I'm definitely going to let u equal x to the 1/2 power. Take the derivative of both sides. I get that coefficient of 1/2 that I don't need, so I'm going to multiply the 2 on the left-hand side. X to the negative 1/2 power can be rewritten as 1 over square root of x, which is kind of convenient because back up here, once I erase this, back up here, I actually have a 1 over square root of x because the coefficient of e is 1. So I'm going to make the substitution. So the 2 is going to go on the outside of the integral. I'm substituting u in place of square root of x. And in place of 1 over square root of x dx, I'm substituting the du. The antiderivative of e to the u is e to the u. That's nice and easy. And then I'm going to resubstitute the square root of x back in place of that and put my plus c and choose my answer. In problem number 8, we have a table of values, and they're telling us that f original is a continuous function on the closed interval from 0 to 6. They give us values of f original. The trapezoidal approximation of f of x found with 3 subintervals of equal length gives you a value of 52. What is the value of k? So k is here. So they're telling me that I'm going to set up 3 subintervals. So I have 1, 2, 3. Trapezoid is area is equal to 1/2 of the height times base 1 plus base 2. I'm going to use that formula 3 times. In this particular, well, not in this, in all cases, each trapezoid is going to have a factor of 1/2. So I decided for my write-up to have the 1/2 factored out. You don't have to factor it out, but you can. I also noticed that in this particular case that the difference from 0 to 2 is 2, 2 to 4 is 2, 4 to 6 is 2. So I'm going to have a common height of 2. So I decided to factor it out, but you don't have to. All right, then I'm going to go to the bases. So for trapezoid number 1, I will have base 1 plus base 2, which is 4 plus k. For trapezoid number 2, I'll have base 1 plus base 2, which is plus k plus 8. That's a plus sign right there. And then for trapezoid 3, I will have base 1 of 8 plus 12. And that's what this is down here. And they said that's equal to 52. So now I'm going to multiply, simplify, combine like terms, and then solve for k and get a k value of 10. In number 9, a particle moves along the x-axis at any time t is greater than 0 with the velocity given. If the particle is at a position of 7 at t equal to 1, so I have the initial condition of 1, 7. What is the position? So remember, position needs position. So I have an initial position of 7. I start accumulating an area at 1, and they want me to stop accumulating area at 2. This integration is what I would call normal because I can just reverse the power rule, and the antiderivative of 4 is 4t. The antiderivative of 6t squared is negative 2t cubed. Increase the power by 1 and divide by the power. Upper bound, lower bound. Be careful with the arithmetic. Now, if this was on a free response question, this would be perfectly fine answer for a free response question. In number 10, we'll see if I can get the graph and the question and the answer. Yeah, that looks pretty good. So in number 10, let's change the color here. We have a rational function that is sort of a mysterious rational function because the value of a is not given and the value of b is also not given. A and b are constant, so a is the coefficient of x squared, b is the constant in the denominator. Which of the following values could be the values of the constant a and b? So we have a graph up here, and notice that I have a vertical asymptote at x equal to 2, and I have a horizontal asymptote at y equal to 3. That's going to have an impact. So to find a vertical asymptote, I set the denominator equal to 0, so x squared plus b equals 0 is how I would find the vertical asymptote. But we know that the vertical asymptote is x equal to 2, which is right here. So I can substitute the 2 in place of x, which is what I'm doing right down here, and I can get a b value to be -4. Now, since the horizontal asymptote is y equal to 3, this rational function is same-heavy, so the horizontal asymptote would be calculated by the quotient of the leading coefficients, which in this case is a over 1. So a over 1 is equal to 3, therefore a is equal to 3. Moving on to number 11. What is the slope or derivative, slope of the line, tangent to the graph of this function at x equal to -1? I'm looking at a quotient, and for some reason I did not capture the work, so I'll do this one for you. Yeah, I don't see it on the bottom. So I'm going to need the quotient rule, and I need to know that the derivative of e to a power is e to the power times the derivative of the power. So y prime will be down, x plus 1, d up, the derivative of the numerator is e to the power times the derivative of the power, minus up, which is e to the -x, d down, the derivative of x plus 1 is 1, over x plus 1 squared. We're substituting an x value of 1, so if I substitute here, 1 plus 1 is 2. If I substitute here, that gives me times -e to the first minus e to the -1 times 1 over 1 plus 1 is 2, and 2 squared is 4. So that gives me -2 minus e to the -1 over 4. That is the same thing as -2 minus 1 over e to the over 4. If I get a common denominator in the numerator, that's over 1, that'll give me -2e minus 1 over 4 over 1. I have a mistake somewhere. Let me figure out where that mistake is. Okay, so I found the mistake. So let me back up here. My eraser. So I was substituting the value of 1, and I did that. Right here, when I multiply, I get -2e minus, and since this is e to the -1, I'm going to make that 1 over e over 4 over 1. I'm going to get a common denominator of e in the numerator. So if I multiply by e, I get -2e squared minus 1 over, I've still got a mistake in here because that's not giving me any of these answers. Daggone it. Okay, found the other mistake. The moral of this story is not to go fast when you're doing your work. Let's see if this takes care of everything. So you probably already know what the mistake was. When I did down d up, I dropped the negative right here, e to the power times the derivative of the power. So let's try this one more time and see if I can do my work. So 1 plus 1, substituting 1, is 2, times -e to the -1, substituting 1, minus e to the -1, over 1 plus 1 is 2, and 2 squared is 4, and that's over 1. So -2e to the -1 minus e to the -1 is -3e to the -1 over 4 over 1. That's the same thing as -3 over e times 1 over 4, which is -3 over 4e. So this is a case where having the answers saved me from making a mistake, whereas if I had been on a free response portion, I would have made a mistake and probably not have recaptured that. In fact, I made a couple of careless mistakes. All right, going to number 12. We're given a derivative of 2 over x. We know that f of e, an initial condition, is equal to 5, and we want to know f of e original. So we need we need f original, f of x. So we're going to anti-differentiate, and we can use this value right here to find the value of c, or we could write it as an initial condition problem either way. So I find the antiderivative of 2 over x. Remember, the antiderivative of 1 over x is ln of the absolute value of x. And then there's my plus c. I'm substituting the given x value of e to the 1/2, and I'm substituting the y value of 5. E and ln undo each other. They're inverse operations, and that leaves me with the 1/2. 2 times 1/2 is 1. Subtract 1 to the other side, and the value of c is 4. And so I can substitute that back into for f of x. So this is f of x right here. And then I can substitute the value of e. And the ln of e, right, or the absolute value of e is e, and the ln of e is 1. And 2 times 1 is 2, plus 4 is 6. All right, moving on to 13, and number 13, we are looking at an antiderivative. I could try u substitution, but it won't work because if I let u equal to 3x squared, if I let u equal to x cubed plus 1, I get a 3x squared that doesn't have anywhere to replace. So the key here is squaring out the binomial and turning it into a polynomial, which is what I did here. Square the first, double the product, square the last, and then that turns it into what I would call normal integration using the reverse power rule and a plus c. Number 14, classic, classic, classic. It is the definition of derivative. So it is the limit as h approaches 0 of f of, and this is point specific, c plus h minus f of c over h. So c, the value of x that we're going to evaluate the derivative at, is 2. The f function is e to, if we take the guts out of that thing and put it back to original, the original function is e to the x. So this is the derivative of e to the x at x equal to 2. The derivative of e to the x is e to the x. When we substitute 2, we get e squared. In number 15, the slope field for a certain differential equation is shown above. Which of the following could be a solution to the differential equation with the initial condition 0, 1? So it might be wise to actually come up here and draw your solution curve. And hopefully you can see that the solution looks like that. And it looks like that. So we're looking for a function that produces a graph that looks like that. Now, oops, let me slide this down. Okay, I can get that in there. So I clearly know that I'm not looking at a family of parabolas because the way that the curve levels off and approaches a horizontal asymptote. So I'm not seeing a family of parabolas, I'm not seeing a family of exponentials, and I'm not seeing a family of semicircles. I'm also not seeing a family of cosines because if this were going to turn back up, there's definitely no symmetry going on in here. So it's not cosine of x. And it is actually 1 over 1 plus x squared. And if you're not sure what that looks like, I mean, well, for one thing, we've eliminated a through d. But the other thing is you could plot some points and kind of get an idea of what the graph of 1 over 1 plus x squared looks like. Number 16. This one often gives kids some trouble. So in number 16, we have the first derivative is equal to the absolute value of x minus 2. Which graph, which of these could be the graph of f original? So the slope generator for f is the absolute value of x minus 2. Now let's think about that. So come down here and consider the note. If f prime is equal to the absolute value of x minus 2, then f of x has to be always positive, because f of x has to always be in, yes, f of x always has positive slopes. And if f of x has positive slopes, if f prime is always positive, f is increasing. So the only two choices are D and E. The only graphs that have positive slopes are D, the graph is increasing, and E, the graph is increasing all the time. But at 2, the derivative, if we substitute 2 into the derivative function right here, 2 minus 2 is 0, and the absolute value is 0, so the slope at 0 is 0, so E has to be the answer. So the slope here, remember, there it kind of levels out if you zoom in on it, and right in here, there's that horizontal tangent occurring at x equal to 2. All right, so moving on to our next problem, number 19. We are looking for when the graph of f original is concave up. We usually think of the second derivative for concavity. So I'm finding the first derivative by the power rule. I'm finding the second derivative by the power rule. I'm setting the second derivative equal to 0 and getting possible points of inflection. I'm putting the possible point of inflection on the number line. This 3 right here is a stray from the next problem. 2 on the second derivative number line, choosing a number on either side, examining the concavity, and making a decision. In number 20, I have a quadratic function, and f is equal to g prime. So the antiderivative of f, which is g prime, so this is really the same thing as saying the antiderivative of from 1 to 3 of g prime of x dx. I'm just replacing g prime with f of x. And so it really wants me to find the antiderivative of this quadratic function, which is what I am doing. I mean, not the antiderivative of the quadratic function. That is the antiderivative. Because the antiderivative of g prime, let's do that here, the antiderivative of g prime is g of x evaluated from 1 to 3, which is what you can see here. So I'm just going to substitute 3 upper bound minus 1 lower bound. In number 21, the graph of f prime, the derivative of f original, is shown from 0 to 10, and the areas of the regions for the graph of f prime and between the x-axis are given, and those are in the graph, and I drew my own graph. What is the so we're doing extreme value theorem, maximum value on the closed interval? So you can see that we have a local maximum at x equal to, what did they call that? What is that number? A local maximum here, f of 0 is 2. So we have an initial condition of 2. They want to know, they want to know actually what the maximum value is, so we actually don't have to have that number. So we have accumulated area of 20. We're losing 6 and gaining 4, so the absolute maximum has to occur at this value, but the maximum value has to include the initial condition of 2. So 2 plus 20 gives me the 22. In problem, speaking of 22, in problem 22, we are trying to decide which of these, let's see, then f has which of the following relative extrema at these values, and then we have to pick some choices. So this is already the first derivative, so the critical numbers are x equal to 2 from this factor, x equal to 3 from this factor, x equal to 4 from this factor. They go on my first derivative number line, choose values, be careful with the arithmetic. and then look at your answers and decide which kind of relative max or min you have. In number 23, the graph of the even function. Remember, even means symmetrical about the y-axis, which means the graph folds over the y-axis. So you can see we have a symmetrical graph here. It consists of 4 line segments as shown in the figure. Which of the following statements about f is false? So we are looking for the false statement. So first it says the limit as x approaches 0 of f of x minus f of 0 is 0. So we can take that apart using limit properties. The limit as x approaches 0 of f of x, so from the left and from the right, we are approaching a y value of 0. So that's where that 0 comes from. And the limit as x approaches 0 of a constant, f of 0 is just a constant, which happens to be 0, is 0, and 0 minus 0 is 0, and that's a true statement, and we're looking for a false statement. In letter B, this is a definition of derivative statement, and what it's saying is the limit as x approaches 0 of f of x minus f of c over x minus c as x approaches c. So it's asking, is the derivative of f of x at x equal to 0 equal to 0? Well, the derivative here is not defined because we see the derivative from the left does not equal the derivative from the right, and that's undefined, so the answer has to be, that's false since the derivative is undefined and not 0. So that's our answer B. In number 24, we have our wonderful classic related rate problem. The radius of a circle is increasing. That means, well, that the dRdt is positive. At a certain instant, the rate of increase of the area rate is dA dt. So notice back up here, I said dRdt is positive. The rate of increase of the area, dA dt, which is what I'm writing here, is numerically twice. That means 2 times. That's what's going on here. The rate of increase of circumference, which is dC dt. So that's me recording all the information that I was reading. The question is, what is the radius? So I'm supposed to find r of the circle at that instant. So I'm starting with what I know, which is starting right here. dA dt is equal to 2 dC dt. So I'm going to take the area equation of a circle, which is pi r squared. I'm going to take the derivative of that by the chain rule, and I'm going to replace dA dt with 2 pi r dr dt. Over here, the formula for circumference of a circle is 2 pi r. I'm taking the derivative implicitly, so I get dC dt is equal to 2 pi dr dt, and I'm going to substitute that in place of dC dt. I'm going to multiply to get the 4, and then I can divide the dr dt's out on both sides. And remember, I'm trying to solve for r, so I divide both sides by 2 pi and simplify, and I get an r value of 2. All right, moving on with number 25. The answer is down here. So in number 25, we have an implicit relationship, which is given here. So I can see some things that could easily get us messed up. And we're going to find the derivative dy dx at a particular value. So we don't have to simplify it out. The first thing I noticed, ladies and gentlemen, and I hope you pay attention to this, is that we have the product rule going on for the first term. So when we find the derivative, and it's below at the bottom of the page, we have to do product rule. So that product rule is occurring here for the first term. All of that is the derivative. Let me write that down. So we have x squared y minus 3x is the implicit relationship, y cubed minus 3. And so then you can see that all of that is the product rule derivative for the first term. The derivative of 3x is 3. The derivative of y cubed is 3y squared dy dx chain rule, and the derivative of 3 is 0. Then what did I do next? I got my dy dx terms together by subtracting the 3y squared, and I subtracted the 2xy to the right side, and I got dy dx by dividing, and then all I had to do at that point was substitute my numbers, and I got a value of negative 7 over 11. Number 26, we have a function, x is greater than 0. We have the first derivative and we have the second derivative. Which of the following is true? So we're looking for information about increase, decrease, concave up, concave down. So the first statement says, for x is greater than 1, f is decreasing. So for f to decrease, f prime would have to be negative, and the ln of 1 is 0. And it says we're greater than 1, so greater than 1 would be positive over a positive. So we can't have anything where f is a decrease. The next three, f is increasing for c and d, and e is a little bit different interval. So I'm going to focus on c and d and see if I can eliminate now thinking about the second derivative. So for the second derivative, both of them have x is greater than e. So I'm going to substitute, if I come back up here, the ln of, if I put e in here, the ln of e is 1. So 1 minus 1 is 0. So if x is greater than e, the ln of, okay, I lost my place. The ln of a number greater than e is greater than 1. So that would be 1 minus number greater than 1. That's negative, so we're talking concave down. So let me look carefully. F is increasing and concave down, which is C, and I don't need to read anything else because I have my answer. 27, FTC Part 2, we have a function that's defined to be the derivative of a definite integral. So we're going to take out the t. Now be careful right here. We're going to take out the t, put in the new function of 2x everywhere that there is an x, and multiply by the derivative of the new function, then substitute in the 2, and we get 2 square root of 12 when we simplify. And then lastly, on this particular test, they do ask us to find the derivative of inverse sine. So remember that that's going to be u prime over square root of 1 minus u squared. So the derivative of 5x, so u is 5x. The derivative of u is 5, so it can't be a, it can't be d, it can't be, even though this is cut off, and I know it's cut off on your paper, it can't be c because that's negative 5, and it can't be b because there's no square root. So even though e is cut off, it has to be e, and you can see my work here. So again, this practice test is a lot of little small concepts that you will use on the free response questions.